principle of mathematical induction. Mathematical induction is used to prove whether a generalization is true or not. It is carried out by a formal set of steps that must be followed each time. To prove something by mathematical induction, you should follow the steps below. Step 1. Under required to prove, state what has to be proved. Step 2. Prove that the statement is true for n equals 1. Step 3. Assume that the statement is true for n equals k, where k is some general member of the positive integers. Step 4. Show that it necessarily follows from your assumption that the statement is true for the very next case, which is n is k plus 1. And step 5, make a formal statement that, by the principle of mathematical induction, blah blah blah, what you've proved, and put in the statement, followed by QED. Use mathematical induction to prove the following. So we're required to prove this. Now we need to prove that it's true for n equals 1. So if we look at the left-hand side, that's just 1 over 1 times 2, which is a half. If we look at the right-hand side, that would be 1 over 1 plus 1, which is equal to a half. So we can say that it's true for n equals 1. The next step is to assume for n equals k. So in other words, 1 over 1 times 2 plus 1 over 2 times 3, and so on, up to 1 over k, k plus 1, is equal to k over k plus 1. So we're assuming that's true. And then we need to go to the next case. So we can get to the next case by adding the next term to each side. So this is 1 over k, k plus 1. The next case would be 1 over k plus 1, k plus 2. And that's going to be equal to k over k plus 1 plus 1 over k plus 1, k plus 2. Now if this is true, and that's what we're assuming, this must be true because all we've done is add this term to both sides. Now let's have a look at this right-hand side. Let's put it over a common denominator. That common denominator would be k plus 1, k plus 2. So I've just multiplied top and bottom of this by k plus 2. Now that we have the same denominator, we can of course put the fractions together. So we have k, k plus 2, plus 1, all over k plus 1, k plus 2. Expanding the top gives us k squared plus 2k plus 1 over k plus 1, k plus 2, and that's equal to k plus 1 all squared over k plus 1, k plus 2. Can cancel that with one of those, and that gives us k plus 1 over k plus 2, which is this with the k replaced by k plus 1 and k plus 1 replaced by 1 more than k plus 1, which is k plus 2. So if this is true, we've shown that it necessarily follows for the next case, and all we need there is the concluding statement. Use mathematical induction to prove that for all positive integers n, the sum of any three consecutive integers is divisible by 3. So what are we required to prove? n plus 1 plus n plus 2 would be 3 consecutive integers. We want to show that that's a multiple of 3, so we'll say 3m, where m is a positive integer. Is it true for n equals 1? So that would be 1 plus 2 plus 3, which is 6, which is 3 times 2. So it's definitely true for n equals 1. Then we're going to assume that it's true for n equals k. Should put 4 there. Assume true for n equals k. So what we're saying there is that k plus k plus 1 plus k plus 2 is equal to 3a for some a which is a positive integer. Now let's look at the next case, which is n is k plus 1. So we'd have k plus 1 plus k plus 2 plus k plus 3. That's equal to k plus 1 plus k plus 2 plus k plus 3, which we could write as k plus k plus 1 plus k plus 2 plus 3. K plus k plus 1 plus k plus 2 is 3a, so this is 3a plus 3, which is 3a plus 1, which is a multiple of 3. A plus 1 must be a positive integer. So all we need now is our concluding statement by the principle of mathematical induction, and so on. And we're now in a position to do this exercise 7.07 on page 274.